Good morning, everybody. Welcome to the first session of the day, which is titled Leakage. We have three presentations in this session. The first one is titled Distribution of Signal-to-Noise Ratio and Application to Leakage Detection by Mathieu Denot, and Mathieu will give the talk. Stage is yours.
Okay, thank you, Mr. Speaker. So I'm Mathieu Denot. I work at CLAT in the IT CEF of CLAT in Grenoble. This is a IT security evaluation facility. So I will present my work on the distribution of the signal-to-noise ratio and application to detection leakage. So first, I will present the context that was already discussed by Francis Olivier last evening in his talk about leakage detection. Then I will outline our contributions, which are in two parts in the paper. First part is dedicated to the distribution of the SNR, and with validations, of course. And then we use these models to analyze the sampling complexity of various decision metrics that can be used for leakage detection. And then I will conclude. So leakage detection, as it was already discussed last evening, is when the device process sensitive data, we want to know whether at the output of the acquisition process, for instance with power consumption or electromagnetic radiations, the signal contains only noise, or also, in addition, one part which is linked to the sensitive data X. So the leakage is modeled as a function of X, which is the sensitive data. So the detection itself is an hypothesis testing. We have two hypotheses. H0, there is no evidence of leakage, and H1, there is some leakage, but it depends on some model. We have to make a leakage model assumptions. And the main assumptions are the Hamming weight model and the byte value model. The byte value model is the most generic because it doesn't make any assumptions about the real leakage. What will be important in the remaining part of the presentation is we define the number of classes. Classes is a different number of outputs of the leakage function F. So for instance, for the byte value model, we have 256 outputs possible. So we have 256 classes. And for the Hamming weight model, if the sensitive data is encoded over H bits, we have K equal to H+1 classes. So in order to implement the detection, we need to have metrics. And we use, there are very common metrics in the literature with the SNR correlation, which is named in the presentation row test. We have t-test, key-to test, mutual information. I will not talk about mutual information in this talk. And usually we take the measure, we define the detection threshold, and if the decision metric is above the detection threshold, we decide for instance, for hypothesis H1, there is some leakage, and if it's below, we assume there is no leakage. The problem is false positive and false negative. False positive are also known as false alarms. This is when you have only noise, the decision metric will be above the thresholds. So you will decide for leakage where there was only noise. And on the other hand, false negative is when you miss the detection. So what we expect from a leakage detection method? Of course, we want to have a good detection probability, but we want to have also low sampling complexity because we'll save processing time. We also, in addition, want to have sometime information about exploitability of the leakage. For instance, the SNR and the correlation are related to the success rate of an attack. So this is informative for us to know if it will be interesting to continue to implement an attack given the SNR. On the other hand, the t-test and key-to test give only information about the presence or absence of leakage, but not about exploitability. We also want to control the reliability of the detection, so control the false positive and false negative rates. To do so, we need to know the theoretical probability detection of the decision matrix. So this is what motivated our contributions. So we have two parts. The first part is dedicated to the computation of the distribution of the probability density function of the SNR for the two leakage model, byte value and Hamming weight model, and for the two hypotheses, H1 and H0. We provide some Gaussian approximation and also non-Gaussian approximation for hypothesis H0. And in the literature, there were only for hypothesis H0, it was known that the PDF of the SNR under the byte value model follow F distribution, but there was no information for the other cases. So this is our first contribution. Then we use this result to evaluate what is the sampling, to work on the sampling complexity. And we fix the false alarm and misdetection probability. We have a given SNR, and we want to know what is the number of traces that is required to detect an effective SNR theta, given a false positive and false negative rest alpha and beta. And we ended with a simple formula, which is product n theta is a function only on the false positive and false negative rates and the number of classes. So we did this for the SNR, for the two leakage model, and we extended to the raw test. And in the literature, there was already this kind of result for the t-test. And this allowed to compare the decision metrics for leakage detection based on the same parameter, the SNR. So, okay. So for how do we derive the distribution of the SNR? So we started with the leakage model, which is a function of the sample is a function of Fk, which is the contribution of the class, plus an additive noise, which is assumed to be a white Gaussian noise with variance sigma squared. In theory, the SNR is the variance of the signal part divided by the variance of the noise part. But how do we do in practice? So in practice, we have a set of acquisition traces. We classify them according to the value of the sensitive data. So for each class, we have the number of traces. We have the index of the traces. So we are able to compute the mean and variance of the signal within each traces, each class. Then we can compute the overall mean, and we can estimate the signal part and the noise part, S and B. In my talk, I will forget the at. When there is the at, this means estimation, but I will not repeat at every time. So we compute this S and B, and taking the ratio, we have the SNR. So in the paper, we start from the distribution of Tn, and we derive the PDF of all the intermediate value, the MK, VK, M bar, S, B, and eventually the SNR Z. So I will jump to the result. So for hypothesis H1, when there is some leakage, we have an assumption which is valid in practice. We have a large number of traces. And we also assume that we have a large number of classes, which typically happen for the byte value model. So in this case, we find that S and B follow a Gaussian distribution. So Z is a ratio of two Gaussian random variables. And it is known that this PDF is given by this formula, which is not very nice to handle. So when we add the approximation of a small SNR, we ended with a Gaussian approximation, which is very easy to handle when we look at the value of the mean and the variance here. So now for hypothesis H0, B still follow Gaussian distribution. We observe that if we have a very large number of traces, B is almost deterministic. it's almost equal to sigma squared because the variance is very, very small. So, but on the other hand, S follow more complicated distributions. So if we assume that, which is given here, if we assume that B is equal to sigma squared, then the SNR is approximatively a scale version of the distribution of S. So this is the generic result for hypothesis H0, but if in addition we have a large number of classes, then we can reuse the previous approximation for hypothesis H0 and just set the effective SNR theta equal to 0, and it works. So in the paper we have many validation with simulation and also with experimental data which are based on the Cascade V2 database. We have here we measure the SNR at the output of the first mask S-box with 500,000 traces. So we have a small peak, SNR peak here, and we assume this is hypothesis H1 and the remaining part is hypothesis H0. So we evaluate the distribution of the SNR under the byte value model and the Hamming weight 8 model. And we use at least for the byte value model, we use 200 traces per class. We have, for each class, we have a set of around 2,000 traces. We selected randomly 200 traces. We do a measurement, and we start it again, and we measure the distribution like this. For the Hamming weight 8 model, we assume that we have at least 200 classes for the smallest classes, and when we increase the Hamming weight, we increase the number of traces. So we see that the model fits with the measure for the ASCAD database. And for hypothesis H1, we also have a good matching with the Gaussian approximation. So once we derive these distributions, we want to use it to analyze the sampling complexity. I will explain how do we proceed for the byte value model. So first we assume that we have the same number of traces for each class, which is a good approximation when we have a large number of classes. We define the detection thresholds gamma, and we use the Gaussian approximation for the SNR with the mean and variance given here. When we have hypothesis H0, we just simply set theta equal to 0. The detection threshold can be defined according to the false positive rate given here. So if we know if we set the false positive rate, given the number of classes and the number of traces, we are able to set the detection threshold in advance. Then we use this formula of the detection threshold into the definition of the false negative rates. And we ended with a polynomial. Sorry, there's a problem with the presentation. With unknown is a function, is a variable x, which is n theta. And the result here is the only solution of this polynomial. So we show that the number of traces times the SNR is only a function of the false positive, false negative rate and the class, number of classes. So we did this for the byte value model. We reuse the same methodology for the Hamming weight model. This is detailed in the paper. And this gives us also the idea to extend it to the correlation, the row test, because it is known that the Fisher's transformation of the correlation coefficient follows a Gaussian distribution. When we are in a low SNR context, we have a low correlation. And so the Z transformation is approximated by the correlation and follow a Gaussian distribution. So we can reuse the same methodology, and we ended with this formula, n theta is approximated by A1 minus B1 squared. In the literature, there was already this kind of result for the t-test. So now we validate this. In the paper, we did validation with simulations and also with experimental data from the ASCAD database. Here I will present validation with simulations. So in the simulation, for the byte value model, we use a stochastic leakage model. We set the false positive rate to 10 to minus 6 and false negative to 10 to minus 3. And in the stochastic model, leakage model, the variance of the signal port is equal to 1, is normalized. So we just shift the value of the noise variance to modify the SNR. And we set the detection threshold according to the false positive rate. And we measure the number of traces which is required to ensure that we have the good false negative rate. So if we start from the bottom, we compare the results from the simulation and theory. So at the bottom, we have a t-test. We have a theory and simulation, the two curves superimposed, so we only have one curve. Then we have the raw test with the assumption that we have a perfect estimation of the leakage model parameter. Then we have key-to test, and then we have multiple curves. And in this curve, we observe that we have, for the SNR, we have a good matching between the theory and simulations. And we also added, for the raw test, the estimation of the leakage model parameters. So we divide the set of traces into, we have NC sets. For instance, we use NC-1 set for leakage model estimation, parameter estimation, and the last set for the correlation, and then we shift. So at the end, we will use all the set for estimation and correlation, but always disjointly. So the conclusion here is that the t-test is the most efficient techniques, then the key-to test, and then we have almost the same performance for the raw test and the SNR. We do the same for the Hamming weight model, and we also have a good matching between theory and simulation, except for the SNR with Hamming weight 8 model. This is because for the hypothesis H1, it relies on assumption that we have a large number of classes, which is not met in this case. And the conclusion here is that still the t-test is the best solution. Then we have a difference between the raw test and the SNR. The raw test, we do not need to estimate the leakage model parameter, and it's much more efficient than the SNR. So as a conclusion, we derive the distribution of the SNR for the byte value Hamming weight models. We derive some theoretical models which are validated with simulation and experimental results. We we analyze also the sampling complexity, and we come up with a relationship like n theta is a function of alpha, beta, and k, the number of classes. This allows to have a comparison of the different metrics. I forgot to mention previously that the comparison was also done for the experimental data of the ASCAD database. So at the end, what are the recommendations for us is, if we are only interested in detection, then there's no question we have to use the t-test. If we, in addition, we are interested in exploitability of the leakage detection, if we use a byte value model, it's easier to use the SNR. If we want to test the Hamming weight model, it's better to use the correlation. So I finish my talk. If you have any question, I will be pleased to answer.
Thank you very much. So we have time for questions.
Thanks for the talk and the work. I was wondering, since you have the PDF for the SNR, could you use it for when you want to do a plot over times for the SNR traces? Could you then use it to plot not only the best estimate, but also a confidence interval? like 95% or 99% confidence interval for the SNR?
Yes. Yes, if it's a Gaussian distribution, you can play with it.
Okay, thanks. I think that could be useful in evaluation. So you already know like what is the possible SNR and not just, okay, what's my estimate, which might be off, especially if we have reasonably few traces. We know that this is biased, so knowing confidence interval instead of just the estimate is interesting.
Yeah.
And maybe another question I had with respect to your t-tests. This is assuming that you do 2 classes for the t-test, right?
Yes, 2 classes, and we use class x equal to 0 as a reference classes.
So x equals 0 versus all the other ones.
Yeah, and we have the same number of traces for each class.
Okay, so like half is x equals 0, half is
Yes.
the rest. Okay, thank you.
Any further questions from the audience? I don't see any on the Zoom chat so far. Maybe a question from my side. Could you extend your analysis also to like the evaluation of, let's say, masked implementations, where we are interested in higher order leakage?
I didn't think about it, but I think the distribution may be much more complicated. But it's open work.
Did you on which ASCAD dataset did you try the this SNR distribution?
V2.
And with desynchronization of traces, or?
No, synchronized.
And how would it handle with desynchronized traces?
I expect it won't work because of desynchronization, but I didn't test.
Okay, thank you.
If there's one question.
Yes. So maybe there's the follow-up question would be, do you see any possible extension to outside of vertical analysis?
What do you mean?
What do you suggest if I correctly understood, is you use vertical analysis?
Yes.
And would it possible to extend this to, I don't know, horizontal attacks or other?
I don't know. Honestly, I don't know.
Okay, please let's thank the speaker again. And the next talk will be Quantile, Quantifying Information Leakage, and the presentation is by Gaëtan Cassiès.
So thanks for the introduction. So this joint talks with other colleagues from when I went at Graz. Vidat did most of this work and was supposed to give the talk, but unfortunately he couldn't be here today. So I'm going to present. So here is a setting where we want to do some kind of pre-silicon evaluation of security. So let's assume we have a design, for instance, a mask design, and want to know if there is some chance that it is going to leak. So this is a challenging problem because you have many points in the leakage trace or in the circuit that computes the value. So these many sets of probes. And then like every single probe actually depends on all of your inputs and all of the randomness that comes in. So it can be like a distribution that depends on many independent variables and can be a very highly structured distribution. So that's not necessarily an easy problem. And evidence for that is if you look at masking verification tools that exist. This is just a figure of merit qualitative one plot for 2 axes that we care about in this talk. The first axis is the level guarantee. Like it goes from very strong formal verification to something that's a bit more empirical and is more of an indication like more like leakage assessment or detection tests. And the other one is scalability, so how large of a circuit can you handle? And there is a trade-off in between these. So on the one hand, you have the ones that have like very strong guarantees and that have limited scalability from like a few mass gadgets to a few dozen, hundreds of them. They're like the very well-known in these tools are like Silver, Cocoa, Masswave. And the opposite sides, still keeping like pre-silicon validation, we have ProLit, who is based more on like statistical sampling of simulations of the circuit, and so you can scale to large circuits, but being based on statistics, you don't get the same strong guarantees that you can get with formal verification. And our goal with this talk is to try to move a bit the statistical sampling approach towards stronger guarantees by improving the use of statistics. So that's one of the goals. The other one is, as I will show at the end of the talk, to move evaluation towards a more quantitative approach, so like how much leakage could there be, rather than yes, no answer, is there leakage or not, because maybe a tiny amount of leakage is not an issue. Yeah. So how does it work? That's pretty common for this kind of tool. So you take your hardware design. In this case, you synthesize it to get a netlist, so you get a circuit. You need a test bench. And then we have our tools that generate runner code that run this statistical sampling. Then based on this statistical sampling, we run a few statistics, and then we can give you an outcome on p-values and so on. So these are the two ideas. I already mentioned statistical sampling, and then the metrics that we care about to have the quantitative approach is to use the mutual information. And more precisely, we have confidence intervals for the mutual information. So we can say with very strong confidence, like, okay, if our confidence interval excludes 0, we know there is leakage with a very high confidence. So this kind of upper and lower bound on the leakage. Okay, so just like to bring the classical T-probing model that's often used in tools towards mutual information, the classical definitions of T-probing security that says you are secure, you're T-probing secure, any set of T-probe is independent of the secrets, which in terms of mutual information can be stated as the mutual information between the secret S and the probes X is equals to 0, given some public data like a plain text. And if we go to sampling, this cannot be verified. We cannot check, we cannot have a statistical test that guarantees us that some value is 0. We can just guess, we can exclude this hypothesis, but we cannot confirm it, so we cannot prove security under this definition. So we'll relax a bit and say, we'll be happy if the mutual information is below some very low quantity epsilon. So the challenges for the paper were to build this statistical bound for the mutual informations. That was the first one. The second one is going for this bound of the mutual information to knowing what it means to practical security. So for the standard T-probing model with information equals 0, we have a lot of experience in that. Now, what does it mean if we change a bit the model? Hopefully, we can keep the existing reduction and knowledge on the link between T-probing security and practical security. And the last one is an engineer approach, which is like how do we get a fast simulation and sampling of the circuit to get enough samples to get good confidence intervals. So the first one, I won't dive into the detail. As you can see, the theorem itself is a bit complicated. The proofs involve, for those who know it, sub-Gaussian distribution a lot. The important part in that, if you don't want to read all of it, is that if we take this number of samples, so nd times nx, it's a kind of stratified sampling, but no total number of distribution of samples in this product, then the confidence interval for the mutual information is 1 over nx plus the square root of 1 over nd. So that means that the size of the confidence interval shrinks not that fast with the number of samples, which means that we need many samples, as we will see later. But still, we have these guarantees on the bounds, and we can get pretty high confidence. So the second challenge is this like more realistic leakage model. And there, like, we will use the classical approach, assuming that we have some practical leakage L, which is a function of x. And we will go through the random probing model, which is often used in this reduction between threshold probing and practical leakage. So this F bottom is this random probing function or matching between the actual leakage and random probing function IDP, where IDP just leaks X with some probability P, and with probability 1 minus P doesn't leak anything. So that's really a random probing model, and that's typically used in the reduction. And here we get a nice bound, which essentially says that we scale the mutual information that we have in our T threshold probing bound by the factor of P of this random probing. So this compounds well, and the bound can be carried out in a sort of tight way. So the last challenge is to simulate very quickly. So how do we do that? That's like, could be stated as a general problem of how to make a fast Verilog simulator. The trick we exploit is that we are not simulating any circuit, we are typically simulating Boolean level circuits. Like, I mean, if you have an AES or things like that, you don't have much integers and much integer computation, especially if it's masked. Generally, you have like a lot of bit level operation. So the trick to make that fast on a big workstation is to use slicing with SIMD. So if you use AVX512, you can do 512 simulations in parallel. And then once you get a statistic, you just need to do pop counts of the states. So that's really fast. Then to make it even faster, like the simulator actually generates codes for the simulation, and that's like, then you compile that code using GCC, and so you get very fast C code that's dedicated to simulating one single circuit. And on top of that, of course, you do multi-threading, which gives the kind of optimization. So compared to something like a very fast Verilog, generic Verilog simulator like Verilator, you gain close to 2 orders of magnitude in speed, mainly thanks to this very efficient slicing. So that will be useful since we need many samples. So the result that we have, first comment is you can see on the left column the number of simulation can be like a few times 10 to the 12, and that runs in something like a few hours or like 1 day or 2 days in a big workstation. So that's like not too much. It's really practical to do as a pre-silicon validation. It's anyway much faster than to do a tape out. So coming to the result themselves, so this epsilon column is the size of the confidence interval, and then on the right we have our best estimates. And then we are looking at quite a few designs. We have AES DOM, Prince, threshold implementation of Prince, and then some low randomness masking scheme for the Prince and for the AES. And for the former AES DOM and Prince TI, we looked at variants of the design. So the first row, like we sampled randomly as specified by the designers. And then for the other one, we want to see, okay, but could you like make it cheaper by reusing randomness? So it's a very simple strategy of randomness reuse, probably not optimal, but like just easy to study. We reuse the same randomness for every round. That's this symbol reuse once. And for Prince TI, we have also these things where we use like a set of fresh randomness for one round, another one for the second round, and then we reuse again the first one of the first round. And so we alternate with the randomness sets. So that's a way to introduce weaknesses and to see how our evaluation tools behaves. And the last column is just like you set all these randomness to 0, except for the initial shares. So you still get randomness, and you might get security just from the initial shares. So the results that you can see here is that actually we can prove pretty low mutual information values for the secure designs, but also for some of the tricked designs that actually have been checked to not be secure in the T-probing model. So we use like verification tools like COCO to show, to identify, okay, like there is a leakage bound that leaks some information, but what we could be able to do is to prove that actually there is information leakage, but this information leakage is very low. So that might be an interesting direction for design of future masking scheme, is to look at designs that are not T-probing secure, but are somewhat close to it, so low mutual information. And then you might be able to gain a lot of performance using that kind of designs. And of course, if you don't choose enough randomness, at some point your mutual information goes very high, and there you're clearly very broken. So that's the kind of result that you get for a confidence level that's like 10 to the minus 3, so 0.5%, so 99.9% confidence intervals there. So another way to cast these verification results is to move from this probing security information towards more realistic, and there we assume some bit value leakage function plus Hamming weights. And there we can cast the security level in terms of mutual information bound as a function of the SNR for every single bit leakage. So this is like a Prince threshold implementation. And there what we are looking at is on the top, we see this blue line. So that's the mutual information that you get from a second order attack. So we know a second order attack is possible because this is like only a first order secure masking scheme. So second order attack is always possible. If you get low noise amounts, so like very high signal to noise ratio, you can probe these 2 bits, you get high information, these 2 bits, and you get an attack. So that's not like the most interesting part of the analysis. So where it's more interesting is when you go to lower SNR. So there your second order attack doesn't become that threatening because combining two leaking bits that have each their own noise becomes difficult and reduce the information. So in that left part of the graph, we can see our discussion on like putting no randomness versus putting a bit of fresh randomness. And then we have the orange curve, which is like no randomness, no fresh randomness. That seems like a very bad idea. And then we have the one that reduces randomness at every clock cycle. And the green and the red are bounds for the 2 sides of our confidence interval. These bands are the confidence intervals. So you can see that green is the confidence interval for the randomness reuse for every round. And then the red one is a confidence interval where you see the upper bound and lower bound is 0. So you don't see it in this log plot. And there it shows like that you use all the fresh randomness every time. So that's the same setting as the one we had here. So Prince TI, we have the like always fresh randomness we use at every round, and then no fresh randomness. And there you could see that we have a red cross on the randomness reuse at every round because we can show that there is definitely leakage according to quantile. It can be verified using COCO. And there is a lower bound on the leakage, which is non-zero. But here you see that the lower bound of this green band is actually pretty low. So it might be okay, even though quantiles and other verification tool will tell you that there is leakage, that might not be too much of an issue because in practice, this is low amount of information value. So that's like first order leakage, but maybe not too much of an issue in practice. So that's the kind of thing we can discuss using COCO, using quantile, sorry. So as a conclusion, like masking verification is known to be challenging, yet we can solve it in many cases of interest. You have seen this graph in the beginning, this plot, like there are some regions of the space, there's a Pareto boundary where we can do some things, and this can be really useful as a pre-silicon validation. You don't always need to do empirical validation as a first step. So sometimes you can already simplify your life using these tools. And I think that studying more and more approach to these tools will improve this Pareto boundary and kind of fill the gaps in between and the scope of circuits that you can verify. Also that this quantitative approach of like bounding the mutual information instead of strictly requiring it to be 0 brings some nuance of this notion of security order that we use so often. And I think it's also an interesting direction to study. Thank you for your attention.
Thank you very much. Do we have any questions?
Hello, thanks for the talk. In the table that you had with numbers, the mutual information seemed to be like upper bounded by 1. you have 0.99, but you don't have like, I don't know, 5.3 or something? How's that?
That's because the X is a single bit. So here we work in this probing model, and probe is probing a bit.
Okay, but so if I would look at 2 probes, then my information would go up to 2. Is that
Yes,
correct?
so that's if you were starting to look at second order probing
Yeah.
model, which would be possible using quantile. Yeah.
Okay, thanks.
So I didn't mention that this is only checks at the first order of quantile, and quantile you can do higher order too. Of course, it becomes more costly in computations.
Maybe one question from my side. What's your general recommendation in that regard? Do you think we should look more into randomness reuse because the security price we pay is kind of small, but the efficiency is probably large?
I mean, randomness reuse or lower randomness masking scheme, I think it's an interesting direction, and I see 2 ways of going with them. One is to go a bit into the approach that we have here, or the approach that Barbara presented for the smooth passage of the graph, which is essentially you start from masking scheme, you know it's secure, and then you start doing things for like reusing randomness, and then you try and check and hope that you don't break the design that way, which can work very well. Another solution that can also work is directly design the schemes to have low randomness or PRNG, and there are many theoretical work that show in masking how you can get security which reused randomness or reduced randomness, or like very simple PRNGs like PRNGs that do XORs of a few bits. All of that is our interesting approach, and we should clearly do more of that. Yeah.
Is the tool field agnostic, or does it just work for Boolean masking?
The tool itself currently works on probing bits, but that's not necessarily the big problem, because actually like practical security is about bits, even if you use some larger fields masking. The question is how do you input the bits, because there you need like non-uniform randomness. So randomness in the field, that's the typical challenge in using this verification with like larger fields, especially like prime fields or like non-power of 2 fields, is to generate uniform randomness and feed them uniform randomness. To be honest, I didn't write the tool, Vida did. My expectation is that you can do that as part of the test bench, that you write yourself and feed the randomness and then challenge the distribution that way, so that should be possible, but take that with a grain of salt.
But maybe at the price of decreased efficiency then in runtime? Because you cannot generate the randomness like bit by bit, which is sampling.
Yeah, you need to do a bit of rejection sampling to generate the randomness. I don't know if that will be the bottleneck or not. I guess it depends on how much randomness your scheme uses.
Okay. Any further questions? If not, let's thank the speaker again. So the next and last talk of this section will be Fallen Sanctuary, a higher order and leakage resilient rekeying scheme. And the presenter is Ray Ueno.
Thank you for the introduction. I'm Ray from Tohoku University, Japan. Today I'm talking about a higher order rekeying scheme with provable security under leakage. This is a collaboration with Naofumi, Akiko, and Kazuhiko from Tohoku University and NEC. There are several types of the side channel attack SCA countermeasures, which have been developed for a long time after the first publication of SCA. Masking and hiding measure ones, which protect a given cryptographic algorithm by mitigating and suppressing leakage during the execution of the cryptographic algorithms. So masking and hiding basically can be applicable to any kind of cryptographic algorithms. And so in this sense, masking and hiding translate cryptographic algorithms into secure implementations like this figure. In contrast, leakage resilience error cryptography is another concept of the side-channel attack countermeasures. So in this concept, so we design and utilize the cryptographic algorithms with a provable security in the presence of some levels of leakage based on the leakage model. Here, leakage model plays an essential role for the provable security and its practicality. So, and therefore, so we should carefully determine the leakage model with regard to the required functionality and security goal. So far, LRPRG, LRPRF, and LRA have been developed. So each of which utilizes different leakage model to achieve its functionality and security goal. So in addition, so leaking can be another concept of the LR cryptography. So cryptography, so which presented as the first and primordial concept. So before going to my main topic, so let me introduce the mainstream of current mainstream of the LR cryptography. I mean the leveled implementation. So this is a concept based on the efficient combination of the DPA and SPA secure modules. Here, DPA security means the unbounded secure module against any SCA with an infinite number of traces. So, you know, it's very difficult to achieve such a kind of the DPA security as the DPA secure module and requires a huge implementation cost. Therefore, it is supposed to be used only for limited computation like initialization and finalization. In contrast, the SPA security means a module secure only against single trace attacks. And, you know, so it's much easier to be realized. Therefore, it is supposed to be used for most part of the computation, like the encryption and tag computation, like in these figures. So in addition, leaking is another type of the countermeasure, as I said. So, you know, so side-channel attacks, SCS on symmetric cipher usually use statistical means like correlation coefficient and negative log likelihood on many acquired traces for a fixed key. So this means the success rate of an SCA heavily depends on the number of available traces. Therefore, leaking updates the secret key using a deterministic function called a leaking function G here, such that the attacker cannot obtain sufficient number of traces for a fixed key. So leaking function G derives temporal key from master key and nonce. So in this sense, we want to achieve LR encryption mode based on the composition of the non-LR cipher and leaking. But there are some non-negligible gap between the existing theory and leakage resilience in practice of the leaking. So at least, so we should consider leakage from the leaking function because the attacker can mount an SCA on this leaking function performed in the target module. However, so it can be protected by a concept of the leveled implementation, but the security goal and functionality of the leveled implementation or DPA secure module is clearly different from leaking, so, and contradicts them. So because we want to achieve a security, quantified security without DPA secure modules. So therefore, so we need another security notion and proof based on an appropriate leakage model. However, existing LR cryptography have some limitation in the usage of the leaking. First of all, unboundedly DPA secure module in leveled implementation is unavailable in the real world. So in practice, so this is kind of similar to the leak-free sanctuary. So masking and hiding are developed to achieve such a kind of leak-free sanctuary goal, but the higher order masking achieves it in asymptotic sense, but never achieves the unbounded security with any finite order masking order. So because you know, so higher order masking, higher order SCA can break it if infinite number of traces are available. In addition, two LRPRS have been proposed in the CHES 2012, which may be suitable in the leaking usage. However, they also have some limitation in absorbing sufficient length of the message. It's a kind of a severe limitation in the leaking usage. In addition, so this security of the LRPRF and the leakage is proven based on their leakage models. But the validity of their leakage model is unclear for leaking. While some literature discusses bounded attacker model instead of the unbounded security. So today we present higher order and leakage resilient leaking scheme LR4, which only assumes unbounded DPA secure modules instead of unbounded security. So our scheme is based on such a serial connection evaluation of the independent random oracles, like this figure. So this construction achieves provable security with having a higher efficiency in terms of leaking than the conventional LR cryptography. In addition, for the practical use of the LR4, we present the information theoretical evaluation method to evaluate success rate of SCA on LR4. This is the outline of this talk. So I first explain the concept and the construction of the LR4. Then I present how to use the LR4 in practice based on information theoretical approach, and followed by its validation. Finally, I conclude my talk. So, before presenting LR4, so let me review the existing fresh leaking. So this figure shows the encryption with fresh leaking, so where G is the leaking function. Here, payload encryption E needs only SPA security or bounded security with regard to the leaking frequency. However, leaking function G needs the unbounded DPA security because G is called fixed master key many times. So, I mean, if master key is recovered, the attacker can compute any temporary keys. So, this means this module is compromised. So, we should consider the protection of G. So, and this makes sense for some cases, such as G is much easier to be protected than the payload encryption E itself. But our goal is provable security, so we should consider another way to protect G in this case. So one way may be protect this master key by leaking in a recursive manner. So in this setting, so this first order leaking module is no longer requires DPA security, and SPA or bounded security is sufficient. But however, so you may find, so we need the unbounded security for protecting second order leaking. So we should consider now how to protect this one. So, you know, so one promising way, so I mean, so protecting third order leaking this by to protect this use third order leaking to protect this module. So this is a promising way if we ignore one critical problem. So problem means, so we need unbounded security for the third order leaking. So okay, I'm actually serious. So this is similar to the case of the higher order masking. So because I mean the higher order masking can be broken by the higher order SCA. But I believe the higher order masking makes sense in practice. So what should we discuss here as a security goal, like the higher order masking? So we should consider the lifetime. So I mean the number of secure calls of E here, because unbounded security is impossible to be achieved. So I mean it makes sense if lifetime gets greater, so exponentially by increasing this leaking order. So in fact, so in terms of leakage resilience, this construction has a significant benefit by assuming the unbounded DPA secure modules. So again, so unbounded DPA secure module is unavailable in practice. So recall that, so success or failure of SCA heavily depends on the number of traces of M. So this means so module secure against SCA with up to M traces. I mean the unbounded secure module would be available for some M in the real world. So here, so our goal is so realize leaking such that updating the key, the number of key, updating the temporal key such that the attacker can obtain such that the attacker cannot obtain M traces for a fixed key with only it should be realized with only M-bounded DP-secure modules. And here is our proposal. So this order LR4 consists of D keyed random oracles with M-bounded DBS security. Here, G1 to GD independent random oracles are serially connected. So yes, we employ a tuple of D counters as a nonce. This is essential for the leakage, our leakage model and security proof to observe query rules. Highlight of this construction may be a serial evaluation of ROs. It may be unusual because an RO evaluation is supposed to output an ideal randomness. However, this construction allows for the deriving M to the power of D temporal keys, so while using only M-bounded DP-secure modules and instead of the unbounded secure module. So why is this construction efficient, essential? So the temporal key derivation of the LR4 is represented by the M-valued GGM3, like this figure. So here I set the M equals 3 and D equals 2. So you can easily find I can have 9 temporal keys. I mean, the square of 3, while each intermediate key is used up to 3 times. Here, the I plus first intermediate key is derived as using the ith random oracle counter and intermediate key. So in LR4, I assume the temporal keys are computed and used from left to right in diagram. So I mean the first temporal key, K31, is derived from K21 and K31. K11, sorry. The second temporal key is then derived from K21, derived as like this by incrementing the counter of the nonce. Here, for one evaluation of LR4, so D calls of the random oracle are sufficient, which is far lower latency than the existing LR PRFs. So in addition, we present caching-based information. So I mean, so for example, so in this case, to calculate K32, so we don't have to evaluate K21 because it is already evaluated. So please see our paper for the detail. And security of the LR4 is proven in a promising security notion similar to the existing LR primitives. So our major contribution includes a definition of the new leakage oracle that represents SCA on LR4. I do not explain its detail here, but what is important is that this theorem states an exponential invocation under leakage regarding leaking. So please see our paper for detail and proof. Okay, let me explain how to design LR4 module. So discussing how to design LR4 module, so we should define side channel attack on LR4 module. So we define it here as the attacker wins if at least one key is recovered, so including intermediate keys. So LR4 generates the number of intermediate and temporal keys like in this figure. So for example, if M equals 3 and D equals 2, so attacker can try SCA trials with 3 traces up to 13 times for different keys. And for larger D, so number of generated key gets larger. So while this means attacker can have more SCA trials. So at least one success among multiple SCA. SCS is much easier than one success in only one trial. So M should be determined with regard to the number of trials and the success rate. So I mean the M can be a function of D. So our goal is, so for a given device, a success rate of SCA should be guaranteed to be lower than acceptable threshold. So this threshold is given as a specification. So we present how to tune M and D to satisfy it for a required lifetime. For this purpose, we use information theoretical approach to the evaluation of the success rate. So you know, as discussed in the previous talks today, success rate of SCS heavily depends on the leakage amplitude from the target device. And this is quantified as the signal-to-noise ratio and mutual information. Here, mutual information, IDX, describes so how many bits attacker can obtain at most from one side channel trace. This means the attacker can obtain at most MIDX bit information from M traces. So in the M-bounded SCS. So in this setting, the success rate of upper bound of the success rate of one SCA trials are known as stated in this theorem. So here, chi is the function defined here, and the shape of the chi is described like in the light figure. So given SR, so we calculate chi SR, and we can determine the M and M. So I mean the trace bound for given IDX to achieve an SR. Then I extend this theorem to the LR4. So as I said, we define success rate of SCA on this order LR4 and by AR here. And we proved in the paper, AR is a function of SR, D, and M. And so simply substituting AR to the previous theorem. So we have the upper bound of the success rate on the SCA of the SCA on the LR4, like this. So we use this theorem to determine M and D in practice for given lifetime, required lifetime and IZX. So this is the design flow of the LR4 module. So first, we need to know leakage amplitude as the mutual information IZX or SNR. So at step one, we profile the device. Then we determine the specification, so which is given by the device lifetime and acceptable success rate on the side-channel attack on LR4 as a threshold. And in the next step, so we determine the parameters, I mean the D and M, so such as the specifications is met for given IZX. So finally, we design and implement LR4 module using symmetric primitives. So I mean here, so corresponding to the random oracles and payload encryption. Here, major instantiation of random oracles can be a one-way hash function, such as SHA-3, with a domain separation. And we finally validate the LR4 as a security primitive. So in this table, we evaluate the MD plus 1, M2 the D plus 1, so I mean the key lifetime with some IZX and D, so such that the success rate should be less than 0.01. Here, we confirm that by increasing the leaking order, the key lifetime increases in digit-wide manner, so I mean exponentially. So linear increase of leaking order increases the key lifetime so exponentially, so this validates the LR4 as a security primitive. Here, we only show the small and practical D, but in the paper, we proved the AR converges to 1 as D to infinity. So this means given AR and IZX, so key lifetime is bounded from above, regardless of the leaking order. However, this bound is very large and converge is slow with regard to the practical D. So we can confirm the effectiveness of the LR4 in practice. And LR4 can be combined with existing countermeasures like masking and LRAEs. So masking decreases the mutual information, so it increases the key lifetime as in this table. And LRAE, we can also use LRAE as a payload encryption, so which increases lifetime as the lifetime is not consumed by calling the SPA secure module in the LRAE. So let me conclude my talk. We present higher order and leakage resilient leaking scheme LR4 with some preferable features like provable security and low latency or compatibility with existing countermeasures. So we are now concerning some follow-up works as described here. That's all. Thank you for your attention.
Thanks for the talk. Do we have any questions?
Hi, thanks for the talk. So this reminds me a bit of the ISAP proposal, if you know about that. If you know about that, could you compare them, how these two differ?
Sorry, what to be compared?
How they functionally differ?
From the LRPRF?
Yeah.
So actually, so we'd like to achieve, so in the LR4, we'd like to achieve temporary key generation with number of the exponential to the leaking order, but so at least PRF, so we need to evaluate any kind of message of input bit length, but we need, so for the leaking perspective, so we need to evaluate any kind of input space, because I mean, for example, PRFs can be used for the message authentication code, but our leaking scheme and LR4 are not designed to use in the message authentication code. So this makes a significant difference to be achieved functionality.
Okay, thank you.
One question from me. So you described how you have to analyze the leakage of your device to determine the parameters of your leakage resilience scheme. Yeah. And if I have like a very leaky device, I obviously have a more expensive implementation to protect. You have the same trade-off if you do masking for implementation. So who suffers more from like a very leaky device? Is there like a break point between these two, or is like leakage resilience always preferable?
So actually, so it's you mean masking cannot has a difficulty in protecting very leaky device like IZX equal to 1, right? In this case, but so leaking also has difficulty in the protecting very leaky device. So as I said, so the MD plus 1 is M to the D plus 1. So I mean lifetime is upper bounded for a given mutual information. So and if this mutual information is too large, so it's a bit difficult to achieve such an exponential increase of key lifetime. So therefore, in this sense, our LR4 may have some drawbacks in similar to masking, and difficulty in protecting very leaky device. And actually, so it's I guess kind of open problem to how to protect such leaky devices.
Thanks for the talk. What you presented reminded me a bit of a paper that was at CHES 3 years ago about leakage resilience authenticated encryption that were building of standard AES core processors, so no masking it. And there was, if I'm correct, they were using similar constructions. Do you know that work? And if so, could you compare?
Sorry, I'm not sure about the paper you mentioned. So,
Maybe you can take that offline and I can show you.
Okay, please discuss later.
Thank you.
Any more questions from the audience? If not, then let's thank the speaker again. This concludes the session. We now have a coffee break.